Good afternoon, everyone. Here's another compound projectile motion problem that's similar to the approaches that we used in the previous problems. So here we have a snowball that is rolling off of the roof of a barn, and it's sloping downward at an angle of 40 degrees. So let me actually just draw perhaps the edge of this barn here. And we're told that it slopes down at approximately 40 degrees. We know that the roof of a barn might hang over just a little bit, but I'm going to draw it like this. Oh, pardon me. Like that. And here is something that I think will be helpful. If I draw a gray line here and get rid of some of the parts between it, that's going to indicate where an angle of 0 is. And if I kind of extend the line of the roof, perhaps like this, and I do the same thing where I kind of chunk it out because it's not actually a real extension of the roof, I'm going to call this angle here our downward slope. And actually, let's go this way. Our downward slope. And it's going to be negative 40 degrees. Why negative? Well, it's sloping downward, and we said that this angle right here is our reference angle where perhaps the theta is equal to 0. So it's sloping down at 40 degrees, and it kind of ends roughly at the same spot where the side of the barn is. The edge of the roof, we're told, is 14 meters above the ground. So this distance here, I'll draw with an arrow, this is going to be equal to 14.0 meters. 14.0 meters. And we're told that the snowball has a speed of 7 meters per second as it rolls off of the roof. If I draw the snowball with maybe like a brownish color, like this, brownish reddish, I guess, I will indicate that speed, we'll call it maybe like an initial speed with this green arrow. That's the speed that it's falling off with. And we're told that that's 7.00 meters per second. We're told to ignore air resistance, so we don't have to worry about anything fancy here. And our first task in part A is calculate how far from the edge of the barn does the snowball strike the ground if it doesn't strike anything else while falling. And how would we go about doing that? Well, we would use our kinematic formulas similar to the way that we've done them in the previous problems. And in fact, when it comes to figuring out how far from the edge of the barn, that's essentially like saying, what is the range on the snowball once it comes down and hits the ground? Right? Something like that. And what kinematic formula can we use when it comes to range or like an x distance? Well, here's a familiar one. We know that x is equal to the initial velocity, the x component, times time. And we've actually been given a part of this expression, right? We know that the initial velocity of the snowball is 7.00 meters per second, and the x component of that is going to be cosine of negative 40 degrees. However, we weren't given a time. So we'll label this as our first equation, and we'll have to use another equation to solve for a time and then plug this back in, and then we'll be finished. Since we were operating in the horizontal direction, what I would recommend next is try to find an equation that works in the vertical that we could use to solve for a time. And the one that we're going to apply in this circumstance is this one. The final position in the y direction is equal to the initial position in the y direction plus the initial velocity y component multiplied by time plus 1/2 acceleration occurring in the y direction times time squared. We know that when the snowball hits the ground, that's essentially y is equal to 0. So our final position will be 0. The initial position in the y direction is what? Well, when it's sitting on the top of the roof, right before it falls down off the edge, it's 14 meters above the ground. So we'll change the y initial to 14.0 meters. The initial velocity we said was 7.00 meters per second, but we're taking the y component, so it's actually the sine of negative 40 degrees multiplied by time. And we can say that, the last part, the only acceleration experienced in the y direction is due to gravity. And we know that gravity is negative 9.8 meters per second squared. So I tend to write that as negative 1/2 g t squared. And now we actually have a quadratic expression in t. This is just like the previous problems where we would have to figure out what a, b, and c are. And remember, a is attached to the highest exponent in your quadratic. So a is this minus 1/2 g. B is going to be the coefficient on just the variable itself, so t. That's our 7 sine negative 40. And then c is always the leftover piece that doesn't have any variable attached to it. So just 14. And remember, we're going to use the quadratic formula to solve for the time when the snowball hits the ground. And the quadratic formula is probably very familiar to you at this point. B squared minus 4ac all over 2a. I won't plug this in on the screen, but if you do so correctly on your calculator or what have you, you should get the following positive time, something around 1.292 seconds. You will also get a negative time. It doesn't matter what it is because we're not going to use it. It doesn't apply to this situation. So as long as you get a positive 1.292 seconds as one of your answers from using the quadratic formula, that's perfect. This is the time that we need in this second equation here that we want to plug into the time back in equation 1. That is exactly the whole goal of why we solved for the time in equation 2. So let me kind of remove this here. It's getting a little messy. I'll put 2 back here. And so now if I want to plug this time back into equation 1, what do we get? Well, we get x is equal to 7.00 cosine of negative 40 degrees, and that is meters per second. I'll actually write the units this time. And we're multiplying this by 1.292 seconds. The seconds units will cancel, and we'll end up with meters, which we should, and x, which is the same as the range. Right? It depends on however you want to call this. We can call this r, we can call this x, same thing. What do we get when we calculate this value? Well, I get 6.93 meters. That is how far from the edge of the barn where the snowball strikes the ground. Now, we noticed in some of the previous problems that we should be reporting our answer to the smallest number of significant figures provided in the problem description. So looking at all the numbers, with the angle, we have 3. With the edge of the roof, I also see 3 here. The speed has 3 as well. However, if we go down to part C, we are given some more information that only has 2. How tall of this person is and how far they're standing from the edge of the barn. To be safe, I would just report this to 2 significant figures. And how do we do this? Well, here's 1 significant figure and here's 2, so the cutoff is right there. 3 is smaller than 5, so we round down. And remember, the symbol that I like to use when doing this kind of approximation is approximately equal to 6.9 meters. That is the answer to part A right there. That's how far from the edge of the barn, the range, or X, what have you, whatever you'd like to call it, that's how far it strikes the ground from the edge of the barn. Now, what about part B? We have to draw a bunch of different graphs for this kind of motion. And, thankfully, we don't have to really calculate much if we kind of get the general idea of what these should look like. So let's start off with an XT graph. We know that the T is going to be on the x-axis and the x is going to be on the y. In this problem, in part A, we know that if I go back to our picture here, in fact, I'll even copy this to the next piece so I don't have to go back and forth. We know that at t is equal to 0, the range of this snowball, as it was getting ready to fall off the edge of the roof, it was at x equals 0. So that means on an xt graph, at t is equal to 0, x needs to be 0 as well. So that's the very first beginning point of what things should look like. And we know that from our kinematic formula, we have like x equals v initial x times t. V initial x is never going to change. It's 7 cosine negative 40 degrees. That's just a number. That is never going to change. But it is going to be multiplied by a number that's getting bigger and bigger and bigger and bigger, the time. So this is just a very linear looking graph where a constant number is being multiplied by another value that is increasing linearly as well. So for our xt graph, it should just look like a linear increase. You don't have to make this look like anything fancy. It should just demonstrate that at t is equal to 0, it starts at 0, x is equal to 0, and then as time increases linearly, x increases linearly as well. What about y of t? Okay, so the graph will have roughly the same shape. Y and t, right? Instead of x, it's just y on the y-axis. But let's think about what happens at t is equal to 0. At t is equal to 0, the y value is 14. Okay? So at 14 meters, rather, if the units of y are meters, it would be at 14. What does the shape of this graph look like? Well, we actually know what the shape is already based on our picture. It looks like a downward parabola. That's the shape of the trajectory, of the snowball as it falls down to the ground. So the shape of this graph is going to be very similar. It's going to look like this, where t right here, we said, was like 1.8 292 or something. Yeah, 1.292 seconds. So it's a downward shaped parabola that begins at y is equal to 14. And another reason that it looks like this is the equation that we use. We said, y final is equal to y initial plus v initial y times t. And since we know that gravity is negative, we can write this as minus 1/2 g t squared. When t is 0, we remember that the initial velocity, or excuse me, the initial position in the y direction is 14. The snowball is just sitting up there at 14 meters in the y direction at t is equal to 0. And then at 1.292 seconds, it hits the ground. And it takes that general shape. And that comes from this. The negative parabola is kind of hidden in this piece of our expression. And because the t squared is larger than all the other pieces of this expression, our general shape takes on that. What about the velocities? This one is actually really easy when we look at the x component of the velocity with respect to time. We said that there's an initial velocity in the x direction of 7 cosine negative 40. Let's try and use another kinematic expression, this one, to see if that changes in time. Plus at. And we'll do x subscripts on this because we're operating on the x velocity. What's nice here is there is no acceleration in the x direction. There's no sideways gravity, if you want to think of it like that. So it doesn't matter what t is because the x component of an acceleration is 0. So that means that at all times, the initial velocity is equal to the final one when it comes to the x direction. So it's always going to be 7.00 cosine of negative 40 degrees, which is a positive number. We don't really care about what the value even is because we just want the shape of the graph. And for all times, if a value remains the same, the shape of the graph will look like this. Okay? So that's for the x component of the velocity. What about the y component? We'll have to change our graph a little bit where we're operating in the negative direction primarily instead of the positive like the last three. This is still time on the x-axis, and on the y, we have the y component of the velocity. At the beginning, at t is equal to 0, there is an initial velocity. It was 7 sine of negative 40. The sine of any negative angle is a negative number. So 7 times a negative number is going to be negative. It doesn't really matter what 7 sine 0 is, since we're just getting the shape of this graph. But we know that at the initial time, there is a negative initial velocity in the y direction. And we know that if we use the same equation that we used here, v final, but in the y, is equal to v initial in the y plus a in the y times t. There actually is an acceleration in the y direction. It's gravity, right? There's no sideways gravity, but there is vertical gravity. So here, our graph is actually going to take on a different shape compared to the last one. So since we have a negative number, 7 sine negative 40, and we have minus 9.8 meters per second squared times time. This means that we are starting with an initial negative number, and as time goes on, we're only subtracting more and more from that number. It's a very linear expression, just like in the x versus t graph in the first one, except the y component of the velocity is just getting more and more negative. So our graph for the y component of the velocity looks like this. And here's all four of them. X versus t, y versus t, v sub x versus t, and v sub y versus t. And they all have their own shape. Now, what about part C? If we go back to part C, we were told that there's a man that's 1.9 meters tall, and he's standing 4 meters from the edge of the barn. Does he get clipped by the snowball as it falls down to the ground? Again, I will excuse me, copy this to a fresh page, and if I draw a man, we'll say he's right here. We are told he was what? 1.9 meters tall. 9 meters. And he's 4 meters from the edge of the barn. 4.0. Will he be hit by the snowball? So, what do we want to do here? It's almost as though we want to see if the man gets clipped in the head by this snowball as it falls down. Perhaps the trajectory of this is a bit over-exaggerated. What we're checking for is, does it do something more like this? Hit him in the head as it falls down. Or does it clear him entirely? So let's just get rid of this. And let's proceed by doing the following. We need to check the snowball's y value at x equals 4 meters to see if this guy's head is clipped. So if I write the following, x equals v initial x times t. I don't know the time that it takes for the snowball to cover 4 meters of horizontal distance, but I know everything else in this equation, so let's solve for t. The x is 4 meters, 4.0, and we know that the initial x component of the velocity is 7.00 cosine negative 40, and we're multiplying this times time, and I'm going to solve for time. So 4 divided by 7.00 cosine negative 40. I'm not going to plug this into a calculator. I'll just kind of leave this for now. But what my plan is to take this number and plug this t value into the following equation. Y final equals y initial plus v initial y component times time minus 1/2 gt squared. The time is going to be this number, and we are going to calculate what the final y position is to see if it's 1.9 meters or something like that, just to see if it hits this guy's head. What are we going to plug in here? Well, the initial y position of the snowball, remember, was 14.0, and the initial y component of the velocity was 7.00 sine of negative 40 degrees. And for t, I'm plugging in that expression of 4.0, 7 cosine of negative 40, Okay? And then we're taking minus 1/2 the value of g, the 9.8 meters per second squared, and then the t, remember, is that same expression, 7.00 cosine -40. And remember on the last piece here, the t is supposed to be squared, so don't forget to throw squared on there. And what do we get when we plug all of this into a calculator? Well, I get 7.91 meters. And you don't have to approximate anything here because we're just checking to see if this guy gets hit. And at 4 meters away from the edge of the barn, this snowball is well above where the guy is. In fact, it might be, said it's like located somewhere around maybe here. Okay, a little bit above, halfway between the ground and the roof of the barn. So something like that. Doesn't really matter where you want to place it. Just know that this guy is fine. He's not going to get hit at all. So the answer to part C is just he will be fine. Okay? No injuries today. That's good. And here's our justification for that. Right? And that's it. Part A, B, and C done of the look out below snowball problem. Thanks for watching.